we'll finish what we tried doing last time, and then we'll. So what we did last time works for arbitrary in all dimensions, but what we well, apparently the dog agrees, which is reassuring. Anyway, so the part we started last time works in all dimensions, but the next step is only valid in dimension 2. And in dimensions other than 2, it's also valid, but the result is slightly different. We'll say something about it. Okay. Well, first of all, let's review what we started to prove last time. Well, we did prove the following thing: by mod C and Chi is the embedded Bordism group. And we started proving the next statement which we needed in order to prove the Madsen-Weiss theorem, namely let me assume both in this statement and the next one, let's assume that k is greater than 0, and we started proving C and k is the loop space of C and k plus 1. Okay. Now, the statement we started to prove is slightly different. Let me recall the statement as well. The classifying space of M and Chi is the same as or homotype equivalent to the connected component of the empty set inside Cn k plus 1. Now,
what remind me what is the k doing?
Let's ask the audience more generally. Does any of the notation make any sense whatsoever? Let's revise the notation. Okay. It's almost okay. Okay, so let's start with n. n is the dimension of the ambient space. Rn. Now, what about d? D is the dimension of D is the dimension of the manifold, the mapping translucent of which we want to say something about. K is well, K is just a parameter. Let's try to remember what C and K is, and then we'll also understand what K is. So it's the space of all properly embedded d-dimensional submanifolds of Rn, which in fact live in Rk cross 0, 1 to n minus k. So in particular, when we project those submanifolds to Rk, we get the proper map. Okay. Now, do the rest of the symbols make any sense, or sort of make sense, or make no sense whatsoever?
What is n?
Okay, n is the Moore version of C and K. Now, what is the Moore version? C and K is a sort of a monoid. Namely, if we have 2 or 3 manifolds or 4 or 5 which are inside C and K, we can compose them by just putting them next to each other in the K plus first coordinate. And by the way, people should pay attention to what I'm saying, because it could be Kth coordinate instead of K plus first and so on. So please pay attention. So the operation is juxtaposing in K plus first coordinate. Now, and then we want to make a Moore version which means we let in the Moore version we let the k plus first coordinate to be anything from 0 to some positive real number a, and then we get a strictly associative monoid, and then we take the classifying space. And philosophically, C and K and B and M and K are almost the same. Okay, does the rest make sense? Okay, now let me try to save the slide. PDF. Okay, so I've managed to save the first slide, which is an achievement compared to what we managed the previous two times. Okay. So last time we started to prove VM and K are homotype equivalent to the component of the empty set inside CM K plus 1, and we constructed a map. From the left-hand side to the right-hand side, and does anyone? Well, it's probably a rhetorical question. I need to review the construction. Okay, but maybe someone else wants to do this. For example, Grisha. Do you remember the construction we used last time?
No, I don't. I'm sorry.
No worries. Does anyone else remember? No, really. Okay. Let's briefly review the construction. And well, let's first of all remember what the classifying space of a monoid is. We take the disjoint union of all products delta p cross mp, and then we quotient out by the equivalence relation, which involves basically the product in the mono. Another way to view this would be to say that we can form a semi-simplicial topological space using the powers of using the Cartesian powers of M, and basically the construction is the same as for groups, and by inspection this construction never uses inverses. It only uses multiplication. So The same construction works for monoids, and we call the resulting classifying space, so now
I think it's also accurate to say that it is a homotopic coherent nerve of the associated topological category.
Sorry, I think this time it was too loud. It used to be. Well, could you please repeat what you said, because I didn't quite get it.
Yeah, I said that it is also accurate to say that the classifying space of a topological monoid is the homotopic coherent nerve of the associated topological category.
Yes, and I think we did mention this. We did mention this when we discussed the classifying space for groups, didn't we?
No, I think we discussed just classifying spaces of discrete groups, so it's a bit different. Yeah.
Okay. Okay. Now, which is a good remark, but let's see if we understand it. Does anyone, apart from Grisha, understand Grisha's remark, and apart from Chris, does anyone understand what Grisha is talking about?
What was the statement again?
Okay, so Grisha, could you please repeat your statement and then explain all the terminology?
Okay, so I said that another way to construct this is to consider this monoid or topological group or whatever as a topological category, meaning that spaces of morphisms have structure of topological space. And then there is a construction called homotopic coherent nerve, which generalizes the notion of a regular nerve to produce a functor from topological categories to simplicial sets, and then we can take a geometric realization, something like that.
Okay. And what is the homotopic coherent nerve?
Well, it's a great question, but basically it's something which is constructed using a thickening of a simplex. So instead of just an ordinary simplex, we consider like a homotopic equivalent thickened version, and then we take an appropriate left Kahn extension to get this construction for all simplicial categories or topological categories.
Okay, so the answer is we construct, we take a category, and then we do what? We can form a semi-simplicial set by taking all tuples of composable areas. We can even make it simplicial, but you're not happy with it, are you? You want to replace it with something. Is this correct?
Yeah,
Yes.
I think Grisha is just observing. So you can write this down directly, which Alexey has done, and it's just the Milnor construction of a classifying space. And Grisha is observing that you can factor that construction into a few steps. So it kind of admits a interpretation in terms of topological or simplicial categories.
Okay.
So the interpretation Grisha gave kind of makes sense more generally for a topological category, not necessarily just a monoid.
Well, yes, we can do the same for basically for any category if we declare n simplices to be the tuples of composable arrows. I'm not sure whether this is related to something Grisha said and to what Grisha said, and basically if this question doesn't have a short answer, I suggest we move on. If it does, then let's hear it.
I think it's fine for now to move on.
Okay. Now, what are yeah? So. Well, what are the elements of BM of the classifying space? These are obtained from some elements of what we take the quotient of, and what is it? M and K. So it's K. No. Okay. Now remember that. Let's remember that elements of BM and K live inside inside this product. So the first attempt to define the first attempt to define the map would be just to take the manifolds Mi and stack them together. Sorry. One. The next one will live in A1 plus A2, and so on. You get the gist. And all this happens. All this happens in k plus first coordinate. Now this well, this doesn't quite work because the result, well, first of all, the result does not involve the weights, and since we have those weights, we probably need to use them in some way or another. And second of all, well, the result is continuous on each product, but it doesn't give one a continuous map from the quotient space, because there are several let's recall the structure maps for the classifying space. They're all given by the product in the monoid, apart from the 0th one and the last one. And the 0th one and the last one just delete the first and respectively the last elements of the monoid. Okay. Now the idea is as follows, and I will just write the idea. Hatcher gives some formulas, and I wasn't able to understand what those formulas mean, if anything. So I will explain the idea of sigma, and I will not attempt to write formulas, let alone explain those in Hatcher's notes. Yeah. Okay. Okay, I will first write something on the board, and then we'll see whether or not what I say makes sense, firstly, and secondly, whether or not it's true. Those are two separate things. So, and secondly, my claim is there are two problems. The first one is two problems which make this this union incompatible with the equivalence relation. Firstly, as the first of the last weight, the first of the last elements of the first of the last coordinates of the element of the simplex go to 0, the first, respectively the last manifold disappears from the product. What does this mean? Well, this means when we take the limit in the quotient space, well, the limit will not contain M1 respectively MP, because that's how we define the structure map. Does the first sentence here describe a potential problem? Well, an actual problem, in fact. Does the first statement make any sense? The limit, where does the limit take place? Here, in this space, in the quotient space. For example, if W0 is 0, which element of the previous product is this identified with? Well, it's identified with something from delta p times -1, comma, the product of all, or the sequence of all MPs except the first one. The structure map just forgets the first element M1. So what happens when I take the limit? I have this. I have this manifold, which is the union of blah blah blah, comma the collection of the W's, and then when I take the limit, the result is identified with something which does not have an M1. And besides, in this definition, we start from 0, so this the something jumps to the left. Because well, it used to be we used to have M2 in the slab from A1 to A1 plus A2, and then we have the same thing, but in the slab A0, A2. Does this make sense? Так, Володя, Гриша,
Sorry.
Имеет ли смысл хоть какой-нибудь вот эти объяснения?
So hold on. If I want to define a map out of this quotient that you've described, you're just using the semi-simplicial structure, right? Just the face maps and no degeneracies.
Yes, I don't want to use degeneracies.
So I guess this is called big geometric realization. And fat. Okay. And so to define such a thing, what do you have to do? You have to define what it is in degree 0, and then check that just kind of the composition behaves well in all the other degrees.
Yes, so basically I take the space we have before we take the quotient, and then I define the map on this space, and then I need to check that the map is compatible with the equivalence relation, which by general nonsense will give me the map out of the quotient space.
But this just means if I have a map in degree, I don't know, p+1, and I have a map in degree p, I need to see that every way to get from p+1 to p commutes.
Exactly.
With a map to C.
Yes.
Okay. And is there a problem? Well, I don't know. So can we write down what the face maps are more explicitly?
Yes, we'll do this on the next slide. But what it says here at the bottom of the page is the first attempt, and it doesn't work for the reasons which are in the upper right corner. So we basically we use the same idea, but we need to modify it a little. Okay, so okay, I'll try to squeeze the structure maps on this slide, because otherwise no one will remember. No, hold on. No, still not what I'm after. Okay. So we have n+1 maps from MP to MP-1, and these are. So we have n+1 maps, which are as follows. The first one forgets the first component, the last one forgets the last component. The intermediate ones just take the product of two adjacent elements. Does this suffice, or should I write it in more detail? So these are the structure maps. And basically
that's fine, but what do you do with the delta part?
Sorry, say again. What do I do with what?
With delta, so you have delta P across NP.
In this definition, nothing, and that's why it doesn't work. So I want to change the definition to take deltas into account, or more precisely to take the doubles into account in some way. So this doesn't work. Well, this doesn't work. So we want to use basically the same idea, and but still we want to have a continuous map. So no. Okay, first of all, let's yes. Sorry again. I've tried to save the slide, and then the program crashed. By the way, if you know, or if you think you know why this happens, please let us know as well. because it's not the first time it happens.
Should I pause the recording?
Say again?
Should I pause the recording?
Should you pause the recording? Should you host the recording? Well, yes, please. Okay. Значит, Гриша, вот можно ли как-нибудь извлечь слайды из видео? Или это слишком сложно?
Ну, единственное, что я себе представляю, это просто скринить как бы куски видео. В принципе, это можно сделать.
Ну, хорошо. Насколько это сложно? Если это занимает там 10 минут, то это одно, если это занимает час, то это другое. В общем, если это порядка 10 минут, то я предлагаю сделать вот эти вот, то есть вырезать там какие-нибудь куски, потому что эти куски, они собственно, всю дорогу там изображаются на экране. То есть, наверное, какой-нибудь из них можно вырезать.
Да, конечно, можно. Я хотел спросить, а вы не хотите использовать вместо Zoom-доски что-нибудь типа Surnal++ или что-нибудь такое, где как бы не будет вот...
Ну, я хотел бы, но я просто не знаю, как.
Ну, на рабочем столе.
На рабочем столе. Так, хорошо. Ну, так давайте попробуем. Значит, сейчас, одну секунду. Так, на рабочем столе. Значит, так. Хорошо, значит, давайте. Так, значит, так, 2 штуки. Так, хорошо. Значит, ну, да, давайте, значит, we will try a separate board, another board, because the Zoom one keeps crashing and it's annoying. I think we've had enough. Okay. Okay. Page background. Okay. Well, it looks like it's working. Now, let's give it a try. Okay. So eraser doesn't erase. Okay, let's see, standard, oh, wait, oh, beautiful. Okay, standard, yes. Okay, well, let's give it a try and see whether or not we fare any better with this one. By the way, does it, okay, save as, export as PDF. Okay, well, let's give it a try. Anyway, no.
Там карандаш возьмите.
Okay. Well, the handwriting's gotten worse, but it's still comprehensible, isn't it?
It's fine and better than I expected.
Oh well.
You don't look like the kind of person who would have neat handwriting, so I'm impressed.
Okay, basically, what we want to do is the following thing. When one of the weights, the first or the last one go to zero, we push the corresponding manifolds undo. We push the corresponding manifolds to minus infinity, respectively plus infinity, in the k plus first forward.
I'm confused about what question we're trying to answer. So there are two separate questions. One is, what are the face maps in the simplicial space? The other is, how do we define a map from the simplicial space to the target? And it sounds like you're answering.
No,
yeah, fine, semi-simplicial. Semi-simplicial. And then the second is, how do we define a map from the semi-simplicial object to the constant semi-simplicial object on C? And it sounds like you're trying to answer the second question. Yes?
Yes. Well, the face maps we used to have them on.
But you told us
on the previous slide. Would you like me to write them?
Well, you told us what the face maps were in the M components, but you didn't say if they depended upon the coordinates in delta P at all.
Delta P. Okay.
I mean, for instance, if I have M2.
So you want the full equivalence relation. Let's write it down.
No.
Deltas do not form a simplicial space; they form a co-simplicial.
They're co-simplicial. It's co-simplicial, right?
Yes, but and M's are simplicial.
Okay, so then this is just the usual way you would form a geometric realization for some kind of simplicial, for instance, the simplicial set, except now M is topologized.
Yes, exactly.
Right.
We form a semi-simplicial space out of the powers of M, and then we do the usual geometric realization. Which is basically as follows. We identify. So if we have or a semi-simplicial space, then what do? We identify for x and say xn and t inside delta n minus 1. We identify delta x comma t, delta ix comma t with x comma delta I of t, where delta I from one delta to the next delta is just the inclusion of the I phase. It's probably bad to use the same delta on the left and on the right, but I think it's comprehensible. Okay, so we use the standard construction of the geometric realization applied to this particular semi-simplicial set. We can always make it a simplicial set without the semi, but we don't want to. And by the way, in all reasonable cases, the two realizations are homotopy equivalent. I've forgotten what exactly reasonable means, but it's easy enough to find out. Okay, now, in order to get a map from the geometric realization to well, to somewhere, we need to have a map from the space before we take the quotient, and then we need this map to agree with the equivalence relation. And well, here is a hand-waving argument how to make the map agree with the equivalence relation. So first of all, let's look at what it says on the board, and let's see whether or not it makes any sense. Chris, Grisha, does it make sense? Doesn't or doesn't it? Or sort of, or it sort of makes sense, but not really. Which one is it?
I think it sort of makes sense.
Okay, so let's recall the following thing. If I have a sequence of manifolds which such that the nth manifold does not intersect the unit ball of radius n, or something like that, then this sequence of manifolds tends to the empty set, and this is part of the topology on the space of all manifolds, and in this argument, this fact is used very often. Now, do we all understand this this statement? No, well, not necessarily. But they are properly embedded, so they're closed subsets of Rn, and the projection to the first key coordinates is proper, and this is all we do. Now, the manifolds are allowed to be non-compact. It doesn't matter, and moreover, we allow and often use the empty manifold. And in particular, when I take, for example, M1 and push it to the left, or well, to minus infinity or to plus infinity in k plus 1 coordinate, in the k plus first coordinate, the limit is the empty set. Okay, now suppose I take not just M1, but M1 union M2. I keep M2 fixed, and I push M2 all the way to minus infinity. Then the limit will just be M2, and so on. And this is the idea we want to use here. Now, how to describe this idea using formulas? Ask Hatcher. Write him an email. Well, try to figure out the formulas yourself. If you can't, email Hatcher saying that his explanations aren't good enough. And this is all I can suggest.
Well, maybe less invasively will be to ask him for overflow.
Matter of well, it's not their fault. It's Hatcher's fault. Well, basically, he tries to make this idea explicit, and then he comes up with some formula. What does this formula mean? Well, I don't know. Anyway, I've just explained my my understanding of this formula, but why exactly this formula does what it should do, I don't know. Chris, do you know?
I mean, no, but I can never do these kinds of things in real time.
Well, okay. So let's say it's let's give ourselves a homework. Okay, where is it? The sound's working now. The formula for B, what is it? Oh yes, B. On page 14. I tried that thing. Anyway, but the idea, well, the idea is straightforward, and I think it is what it says on the board. We get rid of the extra components which we shouldn't have at the limit by pushing them to plus or minus infinity, and by the way, if there are several components, we should push them. If there are several components that correspond to W's that go to minus infinity. Sorry, if there are several components that correspond to W's that go to 0, we should push them all to plus or minus infinity. Depending on basically. Well, suppose we have the first 3 W's that go to 0 simultaneously. Well, we push M1, M2, M3 to minus infinity, and so on. And we do the same with the last 7 W's that go to 0. We do the same with the last 7 M's if the last 7 W's go to 0, and so on. Okay, so does this explanation make any sense? Гриша, имеют ли вот эти объяснения хоть малейший смысл?
Yeah, I think so.
Sorry, I didn't catch that.
I think so. Yeah.
Okay. So well, there's this homework. Apparently, there is a way to formalize what I've just said, and apparently this is what Hatcher does. But I don't know why the formulae do what they're supposed to do. And well, this is homework for everyone, well, including myself, but I've already tried, so I suggest other people try as well. Okay, we need to have a break at some point, and I suggest we stop here, because now we've constructed a map, sort of. We need to prove that this map is a homotopy equivalence. So let's. I don't want to stop in the middle of the proof, so let's have a break now, and then prove something about this map later. Well, let's try to continue. What do we Так, значит, а как здесь, какие здесь, which options do we have? We can't create more pages, I suppose.
Yes, we can. We can also scroll this one with that, so there should be. So the pages are long.
Okay, yes. So let's.
Если удобно, смотреть, можно просто следующую страницу.
No. I think well, I think it's better. Okay. Well. So what? What do we need? We need to do. Undo. Well, we need to prove that we need to prove that the map we've just sort of constructed produces an isomorphism of the homological groups. Well, suppose we have a map from a map from the q-dimensional disk to Cn k plus 1, and such that the boundary goes to the empty set, which is the base point. Well, here the argument is again well, a bit involved, and but let's try to understand it. Okay, let's first focus on the value of the map on one particular t inside the Q, and then we'll see how this helps us to prove that the map is injective on or surjective on the homological groups. We have a proper map from M to R k plus 1, the projection. We have the following go. We want to find sorry, we want to find a eraser. Okay. We want to find a subinterval subinterval of R such that such that M can be joined with let me call this M prime. M prime inside the same space, C naught and K plus 1. Which would be disjoint with RK cross J cross 0, 1 to the n minus k minus 1. Well, why do we want this? No. Well, we want this. No. Grisha, can you see the board?
Yeah, I can see the board.
Okay. So why why do we want this? No. We want to cut M into pieces along the k plus first coordinate and it isn't, not necessarily anyway. Okay. Now, does this girl make any sense? Why do we want to cut M into pieces? Does anyone have any idea? Гриша, зачем нам нарезать многообразие на кусочки?
Не знаю.
Значит, вот давайте мы прокрутим чуть-чуть вверх. Значит, у нас вот есть такое отображение сигма. We have this map sigma. What does this map produce? It produces something which is a union of things stacked one next to each other along the k plus first coordinate. So if we want to show that the map sigma is surjective in some way or another, we need to be able to deform our manifolds f of d to some other manifolds which would have the same shape. Does this make sense?
Yes.
Okay. So what we have is just some submanifold. We don't know we don't know whether or not it's a union of components along xk plus 1. Well, so let's let's see what we can do. Well, there are two cases. There is the easy case. Well, the easy case is when n is no, it's working again. Okay. No. Low dimensional, namely D. Well, let's recall that D is the dimension the dimension of M is less than k plus 1. So there exists a small disk which is disjoint with P of M.
P is the projection.
Yes, P, where is it? It's the projection onto is a projection onto Rk plus 1. So we have the first k plus 1 coordinates, and we call those Rk plus 1. Okay, now
What is J?
J is well, B is a disk, and J is an interval. Okay, now now we want to rescale for some reason. I will now write something which doesn't really make sense, but I will explain. I will explain what I mean in a second. So we rescale B cross J to Rk plus J. Scaling factor. Okay, scaling factor had better be 1. Close to the extremities of J. Let's try to let's try to draw it.
There is no sound. I don't know if you're aware of this.
I have no idea why it keeps turning off. Thanks. So
Yeah, it turned off again.
Thank you. The scaling factor by which we blow up what happens in Rk plus 1 is close to 1 when I'm close to the boundary of J, and it is close to infinity when we are in the middle of J.
Is it infinity? And
what does this mean? Well, this means we take some open ball B prime inside B, and when we are in the middle of over the middle of J, we expand this ball over the whole of Rk, and then what do we get? We get some partially some map which is defined on an open neighborhood of on an open subset of B cross J, and then we apply this map to M, or actually more precisely, we times everything by the identity of R n minus k minus 1. Okay, and then the claim is the result is another submanifold which is properly embedded, but this time it does not intersect. It does not intersect some well, it does not intersect some J prime, or more precisely, it does not intersect Rk, the whole of Rk, cross J prime cross R n minus k minus 1 with the other factor. Now, does this make sense? There will be some parts. What is important is that the result is not necessarily diffeomorphic to M. And there is not even a map in one or the other direction. Okay, does this make sense?
Где у нас
у нас есть какой-то вот такой диск маленький, который живет в РК плюс 1. Значит, M живет над дополнением к этому диску. Но мы хотим еще, чтобы значит, оно жило над дополнением не только к этому диску, а к R. Вот мы хотим вот здесь B заменить на RK. Значит, но так, чтобы при этом значит, это все было бы, то есть, значит, чтобы значит, M не, точнее, проекция M не задевала RK умножить на там, J. Ну, в точности такой же J там нельзя взять, но можно взять чуть поменьше.
Это мы все делаем, чтобы разрезать.
Да, вы помните, там же у нас же вот эти вот, значит, под многообразие, они же там, значит, друг с другом не пересекались, значит, и они были так вот, стояли там друг за другом, значит, вдоль какой-то координаты, как плюс B. Вот мы хотим сейчас изобразить из M что-то вроде, значит, вроде того же самого.
Это вот такие вот разрезы получаются. Ну,
да, значит, M получится, да, совершенно верно. M, well, the result would be M sort of cut along the hyperplane K plus first coordinate somewhere in J. Well, not really, but sort of. Well, because well, we'll see in a minute in which sense we will need to cut M. Гриша, значит, имеет ли хоть малейший смысл то, что сейчас происходит на доске?
Вроде да.
Okay. Now. Well, let's see what happens in.
The sound is off again.
Thank you. It's a slightly more difficult case. Well, D is greater than or equal K plus 1. So in this case, we may no longer assume that the image does not intersect some wall. And by the way, let's note that here we use the fact that the map is proper. Otherwise, well, the image has measure 0, but it could be, I don't know, everywhere dense.
Okay, now let's let's consider the case t greater than or equal k plus 1. In which case, the preimage of every x may be non-empty, but we know it is 0 in the cobordism group, in the embedded cobordism group, basically n d minus k minus 1 n minus k. Hold on. Okay, so this mx, where is it? Well, it's inside n minus k minus 1. What's the dimension? The dimension is d minus k minus 1. Does everyone agree? Well, we project to R k plus 1, and then we take the preimage. The dimension of the preimage is the dimension of the manifold we had, which is D, minus the dimension of the target. Okay. By the way, what does this have to do with? What does? Why is the preimage 0 in this cobordism group?
Is it because we have like a continuous family that eventually becomes empty, and so it's important to an empty set?
Last time we proved that pi naught of C and K is isomorphic to omega d minus k n minus k. The isomorphism is given precisely by taking the preimage under the projection to R chi.
this case, we have M, but M is inside the component of the zero set. So M basically by our assumptions corresponds to the zero element under this isomorphism. So now, does this make sense? Володя, значит, давайте коротко напомним. Значит, у нас вот было такое пространство, красивое C, N, K. Значит, у него есть компонент связности. Вот, значит, мы утверждаем, что значит, группа компонент связности, да, во-первых, компонент связности образует группу. Там не просто моноид, а значит, группа. Во-вторых, эта группа изоморфна значит, группе, вот, которая здесь написана, значит, именно вложенные кабардизмы, то есть группа вложенных кабардизмов, значит, которые там, имеют размерность d минус k, и которые живут в укрытом пространстве Rn-K. Значит, ну, да, давайте построим отображение. Значит, отображение в одну сторону. Не хочет. Well, anyway, why isn't it working? Don't know.
Если стилус интегрит тоже не работает.
Ну, не хочет.
Надо нажать на карандаш, потому что сейчас рука выбрана.
Thank you. Anyway, so the map, no, that was okay. The map takes an M to the cobordism class of P minus 1 of M. And last time we proved that this is an isomorphism. Okay, so we do the same thing here, and just by our construction we arrive somewhere in the class of zero. Meaning in the zero of this cobordism group. Well, this means M bounds a mx does it work? Mx down some W W inside 0 cross R. What is it? N minus K minus 1.
think this is mx, and this is w. Okay, now we want to use it in yes, I think I know why the sounds keeps turning off. Basically, I turn it off. I turn it off myself when I'm moving this window. Okay. Now what's
Новая страница посередине сверху.
Хорошо, можно вот это продолжить?
Тут продолжить нельзя.
Это уже нельзя. Okay. Well, well, something is better than nothing. Let's now see what new pages.
Нет, значит, сверху посередине. Там зелененький плюсик.
Okay.
Ну, тут, да.
Okay. Well, first of all, let's look at this page and see whether it makes any sense.
Что в конце утверждается?
Ну, значит, утверждается пока то, что значит, mx будет границей. Это более-менее потому, что у нас well, this is more or less what we proved last time. Okay. Now. Let me try to squeeze the next step on this yes, well, I'm doing it myself. No mystery there. Let's try to squeeze the rest of the step, because otherwise nothing will make sense. Okay, so then we do what? Which one?
Видимо, опять карандаш сначала, потом.
Okay. Oh, okay, it's working now. So. So we choose a small disk which contains x, well, same as above. Then, by rescaling, we first make sure that m let me put it this way. by rescaling we made sure that M intersected with this small disk. Is mx so mx has dimension mx has this dimension, then we well, the remaining factor will have dimension k plus 1. Okay, so we first rescale the b factor so that in the neighborhood or more precisely over this neighborhood m looks like Euclid, the product of the Euclidean space and mx. Now the let me try to. It's very convenient to use several colors because they can be used simultaneously to an extent. So. By the way, here it's supposed to be a product. So the okay, let's look at these two steps as well. Step one, we well we have this submanifold M, and we choose a regular value x, and then we the preimage of this value is mx. Well, by changing m in a neighborhood of the preimage of a small disk, we can make sure that what happens in this neighborhood is well, looks like rk plus 1 cross mx. Now we use the trick we already used in the simple case, which means we blow up the B component so that the result so that what we have over B coincides with what we have over RK. Now let's have a look at this again and let's ask ourselves whether or not this makes any sense. So let's look at the first step. Does the first step make any sense?
The statement makes sense. I'm not sure why can we do this.
So we have M,
Yes.
which is which is a manifold. We have X, which is a regular value of the projection to RK plus 1. Now we take the preimage. Well, we call it MX. Now well, the first thing yes, so we choose a neighborhood of X such that M has this form over this neighborhood. What does this mean? Well, this means where this isomorphism. Okay, why do we have such an isomorphism? Well, M maps to R k plus 1. This map is well, X is a regular value. Okay, so the map of the tangent spaces is surjective. Okay, now well, this RK plus 1 is well, could be seen as just a subspace of the tangent space that surjects onto RK plus 1. Let's try to draw a picture. Orange. No. No orange. Okay, so okay, so suppose I take 2. Projected to R. Now, what is what is the preimage of a neighborhood of a regular value? I know the preimage of the regular value itself. It is mx. And when I take a small neighborhood, what happens is everything. Well, the preimage gets multiplied by yes, when I take a small neighborhood, the preimage gets multiplied by rk plus 1. Basically, well, let's think a little about it. Because I keep repeating the same thing, but doesn't get any convincing.
Yes, yes.
Значит, Гриша становится ли убедительнее от того, что несколько раз повторить одно и то же, как вы думаете?
В целом, да, наверное.
Okay. So the first step is well, in the first step we only change m over b cross over some small neighborhood of a regular point, and but still we do we do need to do something, because well, in this picture mx might have another part over the same x, which we need to pull away. Okay. Now but then we need to do the second step, which is exactly similar to what happens in the easy case, namely. Okay. Namely, we basically use this picture to rescale m again, so that this time instead of b, I can substitute rk. So we still get something which is non-empty, but this something is Well, it's almost empty. It's the product of a Euclidean space and something cobordant to 0. Okay. Well, let's look at the second step. Does the second step make sense?
Second step.
Well, the second step is very similar to the easy case. We have this B, and we want to. So here we control M only over B cross J, and we want to control it over RK plus J. So we blow it up. Well, not in the sense, in the same sense as in algebraic geometry, but basically we rescale the B so that over the middle of J it becomes the whole RK, and close to the endpoints of J nothing happens. Okay, and then we we need one more step, which is we need one more step. We need to kill this. We need to kill this this part which is shown in green, dark green. What do we do? Okay, we have W and well the boundary of W is M. This okay, I want to use this I want to use this W to to kill this component. Again? What do I do? I do something which is similar to what happens in the proof of this lemma. Okay, I've forgotten what exactly it is. So let's, but still, we need to finish. Well, at least to finish this part, and then we'll see if what we want to do next. So let's. Okay, so Okay, probably the best way to I don't want to use another page. Let me use another chart. So the yes. So the next step after this one would be to there's really not enough room. The next step is to take this W and well, W lives inside I cross Rn minus K minus 1. So let's suppose this I lives in the K plus first coordinates, and then the rest lives well. The rest is the Euclidean space of the last n minus K minus 1 coordinates, and then let me try to figure out again what's happening here. But in any case, we'll finish in about 10 minutes. We're not going to stay here forever. But still, I want him to remember and explain the last part of this argument.
We want to get rid of this.
We want, yes, we want to get rid of the intersection with we want to get rid of the intersection with some slice. Which slice? The slice which is given by requiring this coordinate to be some element of J. And then we okay, so we have this M. Okay, I think yes, I think I understand it now. Okay, so I want to get rid of this rk plus 1 cross mx. And in this picture, mx is shown on the board, and rk plus 1 is the vertical direction. Well, what do I do? So, first of all, I translate mx to, and then I want to join mx cross rk plus 1 and the empty set. What do I do? Okay, suppose well, basically, this this picture sort of joins mx with the empty set. Okay, let me there's okay. Let me take mx and attach mx cross this yellow thing is mx cross I don't know. No, well, it's the other way around. Let me. Mx lives where? Mx lives in the last coordinate. So okay, so we have r chi cross 0, 1 cross mx. I may have messed up the indices, but the idea is I have this I have this brick of sorts or a slab, and I attach RK. I attach basically a cylinder. Well, not exactly a cylinder because I have this RK here, but the way here is supposed to be 0, infinity. Okay, I take mx, I take W. I attach some kind of a cylinder along mx. Now I get something. What is this something? If I push it all the way to plus infinity, I get the empty set, and if I push it all the way to minus infinity, I get rk plus 1 cross mx. And this is how I get rid of rk plus 1 cross mx. Володя, это наши предметы, значит, просто давайте поймем, как избавиться от вот такого произведения.
Я понял, мне кажется, да, как бы горячим убеждением не сформировалось.
Давайте просто там, значит, забудем про m, давайте избавимся от вот этого. Значит, мы знаем, что mx, оно граница какого-то w. Значит, w, оно живет, ну, по определению, оно живет здесь. Значит, давайте мы, значит, теперь его слева умножим на r в степени там k, да, правильно. Ну хорошо, значит, умножили. Значит, теперь, значит, давайте, да, мы, соответственно, вот этот интервал и, он будет k плюс первые координаты вот в том rn, который получится умножение. Теперь давайте посмотрим. Значит, вот, давайте пока даже, значит, ну, там не будем умножать, рассмотрим просто вот эту штуку и. Но там и оно же лежит в r. Давайте теперь присобачим, значит, к вот этой штуке w такой, значит, на этот раз уже вполне себе честный цилиндр над mx. Ну, а потом все там, на всякий случай, умножим на rk. Там, хорошо, значит, присобачили цилиндр. Теперь давайте смотрим. Если мы его двигаем вниз, то вот этот путь, как в прошлый раз, заканчивается произведением mx на r. Если мы его двигаем вверх, то значит, путь заканчивается пустым множеством. Значит, вот, значит, таким образом мы...
Ну, собственно, нам для этого просто нужен был W.
Да, для этого нам нужен был W. So, once again, suppose there is no k, suppose k is 0. And just look at the picture which, so in this picture we have mx and w, and then we attach the cylinder 0 or 1 comma infinity cross mx to w along mx. We get something. If we push it all the way down to minus infinity, the limit is mx cross r. And if we push it all the way to plus infinity, the limit is empty. This is how we connect mx cross r with the empty set. Okay, Grisha, does any of this make any sense?
Yeah.
Well, sorry, we didn't get too far today, but at least we understood something. Now we have, as I mentioned last time, we have two options: go faster but understand less, or keep the same pace as we have been keeping so far, which means we'll understand more, or at least something, but not. We won't go as fast as we could have. Okay, so what are the what do you think? Are we too slow or too fast, not fast enough, and so on? What do you think?
Ну, если мы ускоримся, то я, наверное, вообще ничего не пойму. Поэтому меня устраивает.
Так, ну хорошо. Значит, Гриша, мы сегодня недалеко продвинулись, но мы хотя бы поняли что-то. Ну, по крайней мере, или у меня такая надежда. Вот, значит, мы можем чуть ускориться, да, мы будем понимать меньше. Значит, если у нас желание ускориться.
Вот я хочу зависеть от того, что нас ожидает впереди.
Впереди, значит, сейчас, что произошло? Так, значит, впереди нам нужно закончить все-таки доказательство того, что, то есть мы сейчас провели какую-то подготовку к доказательству того, что отображение индуцирует изоморфизм компьютерической группы. Ну, потом мы это докажем, а потом, это будет простой шаг доказательства теоремы. Вот, а потом нас впереди ждет сложный шаг, он реально сложнее. Потом мы докажем теорему, и вот, собственно, дальше будем обсуждать какие-то там варианты, следствия и так далее. Так, как сохранить? Так, экспорт из PDF. Окей. Так, значит, сегодня у нас, что у нас сегодня? Сегодня у нас, так, что у нас сегодня?
Я заканчиваю запись.
Да, Гриш, значит, да, я думаю, что запись можно